schedule-wise, hopefully you guys all know very well that phase 1 of the project is due this Friday. We'll be handing out sort of phase 2 probably late tomorrow night or perhaps even on Thursday, but it'll be up fairly shortly. I believe we should finish almost everything we need for phase 2 by the end of lecture today. So if you've actually finished phase 1 already, then you'll actually be able to go ahead and get started on that. Maybe just to briefly poll people, anybody finished phase 1 already or getting pretty far along? Okay, great. So I guess that's why you guys are actually here as opposed to the rest of the people that are not here. But nonetheless, if you're watching this on the web, make sure you're getting going on that. So unless there's any questions on either material or project or anything like that, I think we can go ahead and just dive back into where we were the last time. So last time we sort of finished up very quickly on basically this question of what the minimum signal amplitude you need in a high-speed link really comes from. And since we went through that fairly quickly, I just wanted to briefly review that just to make sure it was 100% clear, and then keep on going into some further issues that will certainly be of direct relevance to what you're doing in the project. So last time we had this long discussion about what were the different types of so-called channel responses, which was really just what's the sort of filter that you would see from something that you transmitted to what you'd actually see at the receiver. And I'm showing you here a bunch of different examples of what those responses might look like. And you can kind of see all of them are in some way, shape, or form low pass. But some of them also have these kind of notches that we said come from things like, for example, having these stubs or other, let's say, bad reflections inside of the system. So at the end of the day, we said that, as an example, if we wanted to go at, say, 6 gigabits per second or so, if we looked at these different channels, we'd have anywhere from 20 to 30 dB of loss on our signal. So the question we started looking at was, well, how bad is that? How much of a problem is that really going to cause? And we said that there's really two related issues. The first is just essentially how big are the signals we're receiving at the receiver relative to our noise. And the second is something we'll talk about some more today, the so-called intersymbol interference, which, as I explained briefly last time, was really, given that all these things are low pass, it means that when you send a nice clean square bit at the transmitter, what you get at the receiver will be smeared out in time. So in other words, things that you sent at one time will basically interfere with things that you're trying to send at a different time. So let's just again make sure that we're absolutely clear on this sort of noise and minimum signal side of the question. So what we said there was that, of course, any receiver we build is always going to have some noise associated with it, whether it's thermal noise or flicker noise or anything of that nature. And so the question is just, we need to know how often is it going to be the case that the noise that we have with our receiver, which, for example, could be this probability distribution that I've shown here, is going to be larger than the actual signal we're receiving. And in particular, the picture that we drew was something on this similar to what I'm going to be redrawing on this next slide, where we said that, well, when we build that very, very simple receiver, assuming, of course, this is something like a differential link, then if I look at this so-called I diagram, which just as a reminder was me essentially taking all of the received bits and kind of overlaying them on top of each other in time. And we said that if I really looked at this, this gives me an idea of essentially what sort of on each individual bit, both how wide is it in time, meaning how wide is the sort of region I can sample it and still get, roughly speaking, the right answer, as well as in the voltage dimension, at any given point in time, sort of how far from my receiver threshold is that incoming waveform going to be? Yes? Okay, so the question was about this offset voltage that I mentioned last time, which is I said that any comparator you build always has some offset in it. And so the question was, well, isn't that thing sort of deterministic? So the answer, or the short answer is yes and no. So depending on how you've built that circuit, there could indeed be some truly deterministic offset. By deterministic, I mean that you could have predicted from the get-go that that offset was going to be there. That's certainly possible. As we'll talk about more later on down the road, though, even if you put two transistors right next to each other, and you do everything around them to be exactly the same, they will never be exactly the same in terms of their characteristics. There will always be sort of manufacturing-induced random variations that will cause this offset to occur. Now, having said that, on any one given chip, once you fabricated the thing, largely speaking, that offset is fairly constant. So if you mean deterministic in the sense of not varying in time, that could certainly be possible. But from one chip to another, you may not be able to predict what the value of that offset is. And we'll talk some more about that later on down the road. Okay, so what we said was that if we had our incoming signal here, we had that offset. What we said was that ideally speaking, of course, we wanted to put our threshold kind of right at the center point here. Okay? And by the way, hopefully it should be clear we want to put it at the center, because if we put it anywhere other than the center, you're going to have less distance in the worst case, either in the upper direction or in the lower direction, right? So now, of course, if we add that offset in, and let's just draw that, for example, in blue. Okay, so that would, as an example, push us up in this direction like this. Okay? So now, of course, if we actually have some thermal noise coming into our very simple receiver, which, again, in this case, is just a comparator. If we have some thermal noise coming into it, the picture that we kind of drew is we said, well, we could take that probability distribution of the noise, which, just as an example, let's say it's Gaussian. And by the way, I'm kind of drawing it on its side here, just because it makes it a little bit more clear as to what's going on. So in other words, the sort of, in the vertical dimension here, that's essentially the magnitude of the noise. And in the sort of horizontal dimension here, that's kind of like the probability of the noise being that large. Okay, so this is literally the PDF of that noise, of the noise of the receiver. So if we draw things this way, and we want to know sort of how often we're making an error, then as we said before, what we really need to know is how often is that noise that I've drawn in there going to be larger than the distance between my threshold and that smallest input signal that I'm actually receiving. Okay? So on this picture here, what that basically translates into is the area under that PDF curve that sort of goes beyond that minimum input signal that I've got. Okay? So that's really just a fancy way of saying that, as we talked about last time, if you want to know how often you're going to be making an error, in other words, what the bit error rate is, then really what you do is you look at, essentially, again, the difference between that minimum input signal and your threshold. That's just this V in amplitude minus V offset. And what you're essentially going to do is try and figure out how big that is relative to the sort of total area under that noise curve. Okay? And the way we figure out that total area is through the so-called complementary error function. Okay? So again, we're assuming here it's a Gaussian noise source. And so if we want to know what's the total probability of all of the noise that's larger than this magnitude, you calculate it with the so-called complementary error function. Okay? Yes? Okay, great question. So the question was, well, if I look at this eye diagram, it's kind of fuzzy. And by the way, this picture is actually from an oscilloscope where I did infinite persistence. That's often the way you would get these sort of eye diagram kind of things. So again, the question was, well, wait a minute, this thing is also kind of fuzzy. So how is it that I'm just sort of choosing one particular point and saying that that's the minimum input amplitude there? You're absolutely right. That's not exactly technically correct. This is only correct in the sense that if I deterministically knew that my input signal was always at this magnitude, then that's the number I would use. I'll say some more about this a little bit later on down the road, but it turns out that most of the fuzziness that's in this particular picture is deterministic in the sense that it's very easily predictable, and that the probability of it happening is high enough that for all intents and purposes, you can just treat it as, okay, it's extremely likely that I'm going to get this input signal or this minimum input signal, so I should use that when I really calculate my bit error rate, just because I want to make sure I actually do hit it, given that I'm going to be getting that thing very, very often. Does that answer the question? Or?
Yeah, I guess what I'm wondering is if you're doing this calculation here, you're kind of almost doing in prediction, but you would still have to kind of do that offset calculation based on whatever because you
So I'm not sure I totally understood the question.
So like if you're using this thing here, and I guess you're doing it perhaps before you actually build the thing and look at the eye diagram. In this case, the amplitude might be somewhat higher than what you actually get if you.
Okay, great question. So the question was, well, let's say that I haven't actually built my link yet, and I just sort of predict to have some input amplitude, and then I go and actually build it, I might actually get something smaller than that. Right? That's kind of what you're saying. And indeed, that's correct. Although, as we'll talk about in 1 second, the biggest, or let's say the most direct effect in terms of how big that quote-unquote amplitude will be is going to be due to this so-called intersymbol interference. Okay, meaning essentially how much the bits get smeared out. Okay, so we'll talk some more about that in 1 second as to how we would treat that, what the impact of that would be in terms of how you do the budgeting, so to speak, for your link. But for now, by the way, as you noticed in phase 1 of the project, I'm trying to keep things fairly simple, and that let's ignore the fact that there is that intersymbol interference. Let's just say I have a certain swing at the transmitter, a certain noise at the receiver. I can use this to quickly calculate sort of what the bit error rate I would be getting actually is. Okay? Does that sort of make sense to everybody, or yes?
Yeah. I guess this eye diagram is like a real thing, so it already includes noise.
It includes noise from whatever it is that's measuring this, right? But presumably that's small in comparison to, let's say, the noise that I might care about otherwise. But you're absolutely correct, and just to repeat the question for the online folks, the question was, presumably this measurement includes some noise from whatever it was that was used to measure it. That's indeed absolutely correct. So you shouldn't take this picture, let's say, literally in the sense of this V in amplitude is exactly the one dot that I've drawn at the very bottom there. That's obviously a statistical quantity, but it's really the, let's say, the meta idea of if I have some relatively known input signal and I know the smallest it's going to be going into my comparator, that's what I would use to basically figure out for this V in amplitude. It's a good question. Other questions on this? Okay. So the question you may now be asking yourselves is, so what? Right? So we said that we need the signal to be big compared to the noise. So why don't we just hit the receiver with a bigger signal? Right? Why don't we just up the swing we use on the transmitter and be done with it? Now, at first you may say, well, that's kind of stupid. Like, that's just kind of the easy way out. But having said that, indeed, that's oftentimes exactly what people do. Right? They say, look, I don't want to deal with this. I just want to make sure the darn thing works. I'll send as big of a swing as I possibly can just to make sure it basically works the best possible way it can. All right? Now, turns out the, let's say, simple answer as to why I'm going to argue that you don't necessarily want to do that is the following. So if you remember, we said that when we were dealing with these transmission lines, we typically have to terminate both sides, meaning both the transmitter and the receiver. And usually a common impedance for that is something like 50 ohms. Well, 50 ohms is actually a pretty low impedance. And in particular, if you think about what it would take, for example, to generate a volt of swing with a 50 ohm impedance, at least for the, let's say, straightforward kind of implementation, that takes something on the order of about 20 milliwatts. So I would actually claim that that's a pretty large amount of power compared to, for example, what I could do if I just, on my receiver side, put a little amplifier immediately after I received the signal off of the channel before I actually fed it into my comparator. So just to be totally clear, why is it that I'm claiming that, if I was indeed going to build a receiver that had something like this, with let's just say a certain gain associated with it, and of course there's sort of the termination coming from the transmission line on the other side, why is it that I claim that I can, even for the same total peak-to-peak signal going into that comparator, why is it that I'm claiming that I think I can actually do much better from a power consumption standpoint by adding this amplifier in here versus just driving as much signal as I possibly can in the transmitter? What's really different on the receive side? So by the way, in general, this is just some very simple, Class A or let's say resistively loaded amplifier here. How much current does it take to get a certain gain and a certain bandwidth out of that amplifier? What's that sort of equation we've been using over and over and over again? I believe it was back in homework number 2 and on the midterm. And yeah, okay, so you said it's the tail current times VDD, so that's indeed the power consumption. What is that tail current? What was that? That's correct, but I actually want in terms of things that you know. So let's say that I tell you I want a certain gain and I want a certain bandwidth. There we go. Exactly. Right. So it's just the gain times the bandwidth times V star times the load capacitance. Right. Okay. So that load capacitance, of course, is just coming from the comparator. Okay. So just as an example, in the project, what did I tell you the capacitance was for that comparator? 50 femto. Okay? Turns out that's even actually probably higher than it really needs to be. Okay? So now, again, why is it that I claim that this number is probably a lot smaller than what it would take me to just increase my swing on the transmitter? What does that have to compare against what? Yeah, exactly. It's all about the impedance, okay? Because on the transmitter, I know I've got 50 ohms of impedance. So if I want a volt, I need 20 milliamps. End of story. Nothing I can do. Okay? On the receiver, on the other hand, I'm actually driving only the input capacitance of that comparator. So as long as the effective impedance of that capacitance at the frequency I care about, and we'll talk some more about that in 1 second, but you can imagine that's really just related to the bandwidth you're interested in. As long as that effective impedance is higher, it's cheaper for me to basically perhaps add more gain there than it is to just dump a bunch of extra current into the transmitter's 50 ohm termination. Does this make sense to everybody? Or? So again, in other words, the real key point here is that if you have a system where the impedance is very, very low, then to get a certain amount of voltage swing costs you a lot of power. Whereas if, for example, on the receiver, I can actually get much higher impedances, on the net, I can probably do much better by putting gain in the receiver than necessarily just by putting the maximum swing I can in the transmitter. Okay, now I'm describing this as a unidirectional trade-off. Obviously, there's always a balance point. In fact, that's one of the things that indeed you can play around with in the second phase of the project or even the third phase of the project. But the key take-home message really is that we can indeed do globally much better by utilizing the fact that the receiver has a higher impedance than the transmitter does. Okay? There's another point to be made, which again we'll talk about some more in 1 second, which is that just increasing the transmit swing will never fix the problem of the so-called intersymbol interference. Which, remember, that was just all about the bits being smeared out. Well, if they're being smeared out and sort of fighting with each other, if you make them all bigger, relatively speaking, nothing really has changed. They're all sort of fighting with each other in the same relative magnitude. Yes?
Sorry, what do you think about how the transceiver comes into this in terms of its being lower and improving things?
You mean the transmitter being its impedance lower?
Oh, you mean the transmitter that's... Okay.
Yeah, so I didn't draw the transmitter here, but obviously there would be a transmitter sort of on that side. Yes. Okay. So the bottom line, as I was saying before, is indeed if you can use lower swing than sort of what that, let's say, maximum swing of the technology would imply, then indeed you can actually get lower power consumption. And at the end of the day, the reason that I'm focusing on this problem is that it will actually be a good application of all the material we've been learning in 240. So with that in mind, what I would like to quickly do now is just walk through a few of the, let's say, representative or most important pieces of the circuitry you'd be encountering. First, just so you have an idea of what they look like, but also second, really specifically to give you a sort of, let's say, a little bit of a bootstrapping on the project. Okay? So the first thing that we'll look at is the transmitter itself. And there's lots and lots of different ways to build these, but it turns out that one of the most common ways is really to utilize a differential type of topology. For all of the reasons we've talked about before, right? So being more insensitive to common mode, power supply, and etc. So the most common way that you'd build one of these things looks something like the following. So first, if you'll recall, we said we would like to terminate our transmitter, meaning that its source impedance should be 50 ohms. So we'll do that in this case literally just with resistors. And then what we'll basically do is just build a differential pair that will steer some current into that 50 ohm load based upon the data we're trying to transmit in the first place. Okay? So if I draw this with the sort of connections to the transmission lines, those would be the differential transmission lines going out of the chip. And obviously everything to the left of here is on the chip itself. Okay? So the idea here is quite simple. If I have some bias current, what I'm going to do is, for example, if the data is a 1, I'll steer that bias current into this left-hand side. And if the data is a 0, I'll steer it into this right-hand side. Okay? And based upon that, I'll create a differential voltage signal. So overall, this is a pretty simple way of doing things, right? Nothing really complicated. There are some minor details as to how you really make this work, but very, very simple structure. And so because of that, it is indeed actually a very, very common way of doing things. Also, as I mentioned before, because it's quite robust to power supply noise and common mode, and etc. There is, however, a penalty that you're paying for doing it this way, as opposed to some other ways that you may hear about. I should mention, by the way, this is called a current mode transmitter, because you'll notice what I'm really doing is just taking a current and steering it back and forth into these sort of output loads. Okay? So the penalty that you're really paying here is that if you really want this thing to behave as a current source, and I'll ask you guys, if I really want this, for example, tail transistor down here to act like a current source, what does that mean about sort of the lowest voltage I can put across there? What would that typically be? Yeah, something like K times V star. Okay? And turns out, if you really want the whole thing to behave in, let's say, a good or very robust fashion, you'll typically want whichever one of these switches is on to also actually remain in saturation. So that means that this should also be, in the worst case, something like K times V star. Well, if you think about it, that means that my power supply up over here has to be greater than 2 times kV star plus whatever swing you actually want to get. The reason that's a little bit bad news is that, for example, if you were to compare it against a topology where you were just to make your power supply exactly whatever you wanted your swing to be, obviously you're paying extra power consumption. Basically, you have extra voltage overhead just to keep those transistors in saturation, as opposed to another topology where you just tried to make it exactly have just barely enough supply voltage for the swing you really needed. Make sense to everyone? Or? K is just, if you recall, we talked way back when we talked about current sources, we said we can make some arbitrary factor between the V star and minimum VDS. That's the K in this context. Okay, so nice and simple, but costs you a little bit of extra power. So, by the way, in the next phase of the project, I'll be giving you already a transmitter to start with. It'll be based on exactly this topology, not because necessarily that's the optimum topology to always be using, but just because it's very simple, it's very easy to understand, it's therefore also very easy to build. Okay, so now let's start thinking about the receiver. And the first thing I want to mention a little bit about on the receive side is not necessarily per se the receiver circuitry themselves, but actually how you're going to terminate the receiver. So let's just draw a simple picture to hopefully make it clear what the issue there might be. Okay, so let's say we build our transmitter exactly the way I had mentioned a second ago. So just inside of this box is that differential pair I had drawn. And so we have those 2 pull-up 50 ohm resistors, both tied to VDD. Okay, then we feed those into the differential transmission line. Then on the receive side, it turns out that the most common way to terminate the receiver is again just to use those 50 ohm resistors. And for the sake of simplicity, let's also assume that we're just going to tie those 50 ohm resistors also to VDD. So again, very, very common way of building this thing. So the question I want to ask you guys is, if indeed I do things this way, what does this imply about the common mode going into my receiver? What's that going to be set by? It is absolutely going to be the output common mode of the transmitter, but what is that? What is that set by? Okay, you said it's going to be determined by the current through the resistors. Anything else? Which is indeed the tail current of the transmitter. So I just want, let's say, the complete equation now. And just as a reminder, this is going to be VDD for both sides. Okay. Okay, great. So this is where the confusion gets in. So certainly you're going to be starting off of VDD. Now the question is, how far below VDD do you really go, both in terms of the swing and in terms of the common mode? So just to be totally clear, if indeed I really terminate on both sides like this, and I look back at this original transmitter that I built, what is the net impedance looking into either side of that transmitter? It's 25 ohms. Because there's 50 ohms in parallel with the 50 ohms of the transmission line, which eventually just becomes the 50 ohms at your termination. Okay, so what you actually see here is 25 ohms. Okay? So given that that's 25 ohms, then obviously, our common mode will be set by that 25 ohm resistance. And then the only question is, what is it multiplied by in terms of the current? There we go. It's multiplied by half of the current. Okay? And by the way, just to be, let's say, totally clear, I'll rewrite this in a slightly, perhaps more obvious way. This will just end up being VDD minus whatever the swing is, divided by 2. So now let me ask you guys, is this good news? Is this bad news? Why does this matter? Yeah, that's right. It may not be where you want the common mode to be. And I guess, Rachel, did you have something else you wanted to say? Or? Okay, very similar answer. You're saying, well, look, if the swing is small, then my common mode is going to be all the way up right next to VDD, which again may or may not be where I really want it to be for my receiver. And that's absolutely correct. So the problem here is you really have no independent way of choosing what the common mode actually is. It's completely set both by what the power supply is and by what the swing you're using. And because those two are fixed usually by other things, that may or may not put you where you actually want to be. So because of that, there are a couple of other options that you can come up with. And for now, I'm only going to draw the receive side. So let's, for example, pretend that this is V plus here, and this is V minus. Another, let's say, option for how you might connect this thing would be something like the following. Okay, let's say you take your V plus, your V minus. You're still going to have 50 ohms there, 50 ohms here. And then take those two sides and again, feed them into the receiver. So what's different about this particular configuration? And this is it. I didn't forget to draw anything. So how would this one be different in terms of the input common mode? Okay, so you said that for your common mode signal, your transmission lines are actually not terminated. That's absolutely correct. Let's come back to that. Let's ignore that for 1 second. Let's just pretend from a completely DC standpoint, which means the transmission line, for all intents and purposes, is just a wire. What's different about this configuration versus that configuration? Yeah, basically the 1/2 is gone. In other words, this is lower because now from a common mode standpoint, those 50 ohm resistors don't show up. Right? They're not pulling you up towards VDD. This is just, if you remember, this is kind of like how we drew our common mode sensor circuits. We just said if we put two resistors and a bridge across it, it wouldn't change the common mode. It would just kind of measure what it was in the center point. Same idea here. So in this case, what we did is we played a trick to make the common mode impedance higher than the differential impedance. And because of that, this would shift our common mode down. Now, by the way, this still may or may not be a good thing. Like, this still may or may not really put you exactly where you want to be. Now, before we move on, there is actually the other point that Jethro brought up, which is this means that the common mode is not actually terminated on the transmission line. Right? If you launched a wave into both V plus and V minus together, then when it shows up over here, it would see no termination whatsoever. Right? Nothing would happen. I mean, it would actually reflect off of that termination. In general, that's a bad thing to have happen, because remember, there's no such thing as perfect common mode rejection. So typically, you want to make sure that it is actually terminated. So can anyone tell me how I might sort of fix this circuit with a relatively minor tweak? Okay, so you said that you could bias this to some common mode voltage. That is true, although we have to be a little bit careful in that if you really were to do exactly what I drew there, what's a little bit perhaps bad about this? Exactly. You're sending DC current all the way from here into this point right here. You're absolutely correct. There is going to be DC current flowing through there. But now, obviously, if this is not VDD on both sides, the impedance of that might not be sufficiently low. But you're absolutely right. The same thing is happening in both cases from a DC current standpoint. That is correct. But it does say that if, for example, I wanted to tune this common mode, I can't just sort of choose this arbitrarily, right? If I yank it all the way, for example, down to ground, then I'll have a lot more current flowing through there than I may have otherwise wanted, simply due to that common mode path. Yeah. Okay. So you said actually the next, and let's say final option. So you said, well, look, if I really want to set the common modes independently, then what I would actually do is something like this. I would put AC coupling capacitors in front of everything. Then I would take my 250 ohm resistors, feed that into my receiver, and then indeed, I could put the common mode in the center tap right there. In terms of setting the common mode, this indeed would absolutely work from that standpoint. There's going to be another issue with this particular circuit, but before we get to that, I claim there's one more trick we might be able to play in the center tap here that does not have any DC current, but will at least over some frequency band give you a reasonable common mode termination. Anybody have an idea? There we go. So you said you can put some caps in parallel with the resistors. You have to be a little bit careful though. Are you really going to put the capacitor literally in parallel with the resistors, or are you going to do something else? Yeah, if you put them exactly in parallel, it still wouldn't show up in terms of the common mode. But there is one other way you can connect a cap that will, I believe, do the trick. Yeah, exactly. You can just take that cap and, for example, tie it to ground or to VDD or to whatever your common mode termination point is. So the idea here is that obviously at DC that cap doesn't do anything, but at any frequency where this cap's impedance is low in comparison to the termination resistance, then indeed it will give you a good common mode termination. Because now this will look as if it's an incremental ground at that frequency. Okay, or an incremental, let's say, power supply at that frequency. Okay. So now let's think about this other trick that we played over here. So here we said that if we really wanted to set the common mode completely independently, we could basically just AC couple into our receiver. And indeed, this is a very, very common trick. It works pretty nicely, but there's one thing we have to be careful of. So what does you have to be careful of here? Why don't I just arbitrarily do this everywhere? Yeah, you said the high pass corner. So what do you mean by that? Yeah, exactly. So what's going to happen here is that if I think about sort of the transfer function of that circuit right there, as you said, it's a high-pass filter. And there's going to be some corner frequency below which I'm going to start attenuating my input signals. So in the specific context we're talking about here, which is these high-speed chip-to-chip communication links, let's say as an example that this corner frequency was, I don't know, at a megahertz. Is that okay or not? And by the way, let's just make up some numbers. Let's say that your link is running at, I don't know, 5 gigabits per second. So is it okay to put it in megahertz or not? Okay, so you said probably and sounds fine. So it was indeed a trick question. So now, what's the trick?
Well, if you keep transmitting one, on the side, but you don't look like one anymore.
Codes never have like an infinite number of zeros or ones. Sending bytes, there's like an acknowledge or something.
Okay, so great. So you guys both got it smack on. So what Andrew first said was, well, hey, wait a minute. If I'm transmitting an infinitely long sequence of ones, then indeed, eventually that data is just going to go away. You're not going to see it through that AC coupling capacitance. And then what Paul said was, well, wait a minute, codes always have some, you can't have these infinitely long sequences. You have to have some number of ones before you have zeros. Turns out you're both right. Okay, so in some systems, there is no coding. There's nothing that stops you from sending as many ones as you possibly want. By the way, a typical example of that is something like a memory interface. Because in those memories, they care about every single last square micron of die area. Okay, so they want to spend absolutely zero on doing anything in addition. So a lot of times those are DC coupled and have absolutely no coding on them whatsoever. So if you just happen to be unlucky, you can get really, really long strings of ones. That's not to say that practically you'll really ever get an infinite string of ones, but you could get something that's long enough compared to that corner frequency that you really start losing your data. On the other hand, indeed, if you want to be able to use this kind of trick, which again is quite common, what you'd basically do is you have to specify, well, what's the longest number of either repeated ones or repeated zeros you can get, and make sure that this corner frequency is sufficiently low in comparison to that. Make sense, everybody? Or? Yes?
So in this case where you, on the left-hand side, where you got the capacitor, and you're basically treating it like a sort of like a short and high frequencies, it seems to be sort of running into the same problem as before, where you're not really, you still have that.
Sorry, where you still have the what?
The factor of 2, or is that just because the DC point is still okay, but it's just the AC?
So if I understood the question correctly, you were saying that if I put the capacitor here for this common mode termination of the circuit, I think you're asking, does that still give you the same common mode here, or does it give you something else? And so remember, the capacitor at DC has infinite impedance. So that means that at DC, indeed, the common mode would be lower than it was before. I'm just adding this capacitor in so that at any quote-unquote reasonable frequency, I still have a good common mode termination. Meaning that I don't have an infinite impedance looking into it from a common mode standpoint. Okay, great. Other questions? So if not, let's actually start looking at a couple of things quickly that are really directly relevant to the project, and particularly this phase of the project. So, as hopefully all of you have seen already, the kind of most basic receiver that we could start thinking about would be doing something like the following. So we could take our input signals off of the transmission line. I'm not going to draw the termination, by the way, just for the sake of not getting the figure too crowded. I could build sort of a front-end amplifier and then feed that into my comparator. And it turns out, in case you haven't figured this out already, at least for this very, very simplistic design, probably the sort of easiest and best choice to use for that front-end amplifier there is just going to be something like a resistively loaded differential pair. So something like this. Now, the question you may have been asking yourself is, why did we want to use this preamp? Why did we add that thing in before the comparator? In other words, why didn't we just directly feed the inputs into the comparator? So to fully answer that question, we need to know a lot more about how comparators are built. But for now, let me just state the following, and again, we'll see this very shortly. Turns out that those comparators, in order to really work the way we want them to, typically have quite a few devices in them. And in particular, have quite a few more devices than the preamp does. That really has two implications. The first is that they tend to have a lot more noise. Because if you have more active devices, all of those active devices contribute to noise. And the second, perhaps more important one, is that the fact that there's more devices also tends to indicate that there's larger offset. So at the end of the day, and let me just maybe write that down to be sure it's clear. So a comparator has more devices, and therefore more noise and more offset. And so really all this preamp is doing is trying to essentially attenuate both that noise and that offset. And by attenuate, I really just mean in the input referred sense. So that if, for example, that comparator has an offset of, I don't know, 20 millivolts, I put a gain of 2 into the preamp, then input referred, you now have half of the offset as you used to. And again, we'll see this in much more detail later on the road. It just turned out you can often build this pre-amplifier in a way that costs you a lot less power to get the same input referred noise, offset, and etc., as it would to really build the comparator to meet all of those specifications. Does this make sense to everybody? At least, given my somewhat high-level hand-wavy description. Okay, good. So now, the next question, which again, hopefully you've already been asking yourself in the context of the project, is let's say indeed that you believe me for now that you're going to want to use this front-end amplifier. The next question that you may ask is, well, okay, so if I'm going to build that front-end amplifier, what should my gain actually be? Right? What should I choose for that A in the amplifier? So, by the way, you may have noticed when I handed out the project spec, I said absolutely nothing about what the gain is. And by the way, if you ask me what the gain should be, I will tell you I don't care. It's up to you. So now, the question for you, however, is how are you going to choose? What are you going to have to use to decide what that gain should actually be? Okay, you said noise, offset, what else? Error rate, anything else? Okay, bandwidth we'll come back to in 1 second. But we said noise, and by the way, let's write these down. So we said we need to know noise. We need to know offset. We need to know bit error rate. Power. Okay, power is going to play into this picture in the sense of, obviously, whatever we calculate is going to have a direct implication on power. But I'll put that over here on the side. I just want to make sure we have all the terms that we need to actually write an equation to make the decision. There we go, the input amplitude. Okay, so what's really the equation that you would use to sort of combine all these together to tell yourself, do I actually have enough gain or not? In other words, what's the kind of specification that you're going to check if it's met or not? Okay, so I don't need the actual equation. Don't worry, I'll write that down. I just, conceptually, what is the spec you're going to check? Okay, related to the noise. So by the way, just to be clear, what you were kind of reading out an equation to me. What was that equation related to? Yeah, it's the bit error rate. Okay, so the way you're going to choose the gain is exactly by saying, okay, look, the spec I have is the bit error rate. I don't care about anything except meeting that bit error rate. So all I really have to do is make sure that for whatever gain I choose, and with whatever offset I'm given, whatever input amplitude I have, I better make sure that I'm meeting my bit error rate spec. And by the way, just as a reminder, the easiest way to use that bit error rate spec is not really to do that complementary error function. It's just to say, for example, if you want 10 to the minus 12, you know that your input amplitude minus the offset had better be larger than, for example, 7 times the sigma of the thermal noise. Or if you wanted 10 to the minus 20, it'd be 9.25 4, etc. So in other words, just use that complementary error function kind of as a lookup table to tell you how big this quantity needs to be relative to the thermal noise. Now, before we go on, let's say indeed I used a resistively loaded common source amplifier for this front-end gain stage here. What would this sigma n actually be? What would that be set by? There we go. And by the way, we have to be careful. It's going to actually be square root, just because we're in standard deviation and not variance, kT over CL times 1 plus gamma AV. Well, plus some more. So what's the other some more?
Like 50 divided by our load times 80 squared.
Oh, okay. So you're trying to include the self-loading and etc. You're absolutely correct. You should include the self-loading. I'm not going to deal with that for now, but you're absolutely right. There is some self-loading terms and some other stuff that may pop into the picture. Okay. So you said, isn't there also some noise from the termination resistor? Absolutely correct. You should include that as well. I'm obviously giving you a simplified thing here, but by the way, why is it that, and let me just be absolutely clear, why is it that I may have wanted to point out what that sigma n actually is here? Say that again? Yeah, exactly. The noise actually has the gain in it, right? So you have to be careful when you do this, let's say, calculation or this check, because the gain doesn't just appear on one side, it actually appears on both sides. So obviously, whatever you do, you have to be self-consistent, so to speak. Make sense to everybody? So, last thing that you may have been wondering about is, well, I haven't said anything at all about what the bandwidth of that amplifier should actually be. So, to answer that, and again, let me just draw a sort of simple conceptual picture. So let's say, again, we've got our front-end amplifier here. Let's just call it, the gain of A, feeding into the comparator. And let's say that I'm going to look at 2 points now, and I'll do this maybe in 2 different colors. So in red is the direct input into the amplifier, and in black, let's say, will be the output of the amplifier feeding the comparator. So let's say we're just lucky and we have a perfect channel. So if I look, for example, at the voltage versus time going into my preamp, I've got something, as an example, that looks like this. And by this, I mean, if the transmitter sent a 0, 1, 0, or a long string of zeros, a 1, and then another long string of zeros, that would be the sort of analog waveform going into my amplifier. So hopefully it should be clear that if that amplifier has a finite bandwidth, and let's just say it's a simple first order system, meaning it only has a single pole, then what's going to happen is that at the output, depending upon that bandwidth, you'll get some exponential settling behavior. Right? And of course, as we make that amplifier slower and slower, it'll take us longer and longer to settle out that exponential response. And by the way, my drawing is not perfect there, so don't take it too literally, but hopefully you get the idea of what happens as you decrease the bandwidth. Right? So in other words, in that direction is decreasing bandwidth, or equivalently increasing the tau of the amplifier. So now, you guys tell me, what would be sort of the trade-off to be made here in terms of choosing the bandwidth of that amplifier, in terms of setting the bandwidth of that amplifier? So what are you going to be trading against what? Against the gain. Let's assume that we've fixed the gain roughly. So you are right in the sense of there's going to be some interactions there, but let's assume that we roughly know what the DC gain, at least we want it to be, is, at least for now. Okay. So you said that there's power on one side versus what? Okay, you are right that there's burb, but let's say, yeah, okay, there we go, exactly, right? So what we're really doing here is, I could make that bandwidth like infinitely big, right? At least in principle. But it would cost me a huge amount of power to do it. And the point really is that, of course, if I did it, and let's just draw that example, let's say that I really did spend a ton of power, so that I had really, really great settling accuracy, well, would that really buy me any extra signal? No, not really. Right? Because I've already settled perfectly to whatever the input signal actually was. So that means it probably never really makes sense to make the bandwidth so large that you just completely settle it out and you have no sort of residual settling error whatsoever left. Okay? Turns out there's actually a pretty, let's say, interesting optimization you can do here, where you can try and decide, and you can maybe even see that there's kind of a coupling here. Right? This V in amplitude would actually change as you change the bandwidth of your amplifier. Because as you can hopefully see, there'd be some residual settling error due to the finite bandwidth. And the larger that settling error is, the sort of smaller that amplitude would be. So it turns out you can actually do an optimization to try and figure out what really is both the best gain and the best bandwidth to use if you want to minimize the power consumption for a given amount of input eye opening. I'm not going to walk through that optimization because, it turns out there's a little bit of math involved, and that's one of the fun things that you can do in your own project. But if you want sort of a good rule of thumb, which turns out, by the way, to come out of that optimization, the typical rule of thumb is that you should set the bandwidth of your amplifier to be roughly 2/3 times 1 over the bit period. Okay, that's typical rule of thumb. So just as an example, if you're going at 6 gigabits per second, this would say that you should set your bandwidth at roughly 4 gigahertz. Okay? And by the way, you can go and actually calculate how many tau of settling that implies. You'll see roughly sort of how much settling error it's saying that you want to have, quote unquote, at the optimum. Now, having said that, there's one other thing that I should point out here, which is notice that we've said that for a 6 gigabit per second thing, we wanted to have 4 gigahertz of bandwidth. Why might that sound a little bit funny at first?
Well, if you don't know anything about signals and stuff, then you might think that your bandwidth should always be higher than your data rate.
Okay, so you said you might think your bandwidth should always be higher than the data rate. So this is interesting, because now I want to ask you guys something. What is the bandwidth of a 6 gigabit per second signal? It's half. Why is it half? Yeah, okay, so you said it's Nyquist. What's the super intuitive way of thinking about it? What's the fastest changing thing you can do with a 6 gigabit per second signal? Yeah, alternate zeros and ones. So if I've got a 6 gigabit per second signal with alternating ones and zeros, the period here obviously is not at 6 gigabits per second. It's actually at 3 gigabits per second, or 3 gigahertz, I should really say to be accurate. Right? Because obviously this is 1 over 6 gigabits per second. That's also 1 over 6 gigabits per second. So on the net, you of course get 3 gigahertz of bandwidth. Okay, so the Nyquist rate is indeed always half of the data rate, at least for the simple kind of system that we're talking about here. However, nonetheless, you do indeed need, or at least this first order rule of thumb tells you, you do indeed want bandwidth beyond that Nyquist rate. Because what's really happening is that in time, you want to make sure you settle sufficiently to actually get a very precise sort of value at the end of the day. Or rather, so you don't lose very much of your signal due to that finite settling. Make sense to everyone? Yes?
So is all of this assuming that you're sampling
Okay, great question. So you were asking, well, does all of this assume that you're sampling sort of, let's say, at the quote-unquote right spot, meaning right at the peak where you actually have the most signal amplitude? To zero order, yes. So your question may be related to you're saying, well, look, if I don't really know exactly where I'm sampling, then I might actually have to settle more accurately, because otherwise I'll pick up more input-referred noise. That's a somewhat, let's say, more complex topic in the sense of, to really answer that question, you need to know, first, where it is you're really going to be doing the sampling. And second, perhaps more importantly, what's the sort of probability distribution of where you're going to be doing the sampling, meaning how much jitter you actually have. Because you can imagine, if I have a very sort of clean jitter distribution, I may be less sensitive to exactly, I know exactly what I'm going to get from sampling at that point, whereas if I have, let's say, a lot of jitter, now I do indeed have to sort of average out over that regime around there. Yes?
So in terms of like at bandwidth, talking about wanting to make sure that you can get high enough when you're settling, it seems like you could also sort of essentially increase the gain quite a bit. So because you're not settling, but you're going to get kind of closer to the point anyways. And I guess looking at sort of some preliminary tests and stuff like that, I mean, once you start dropping off, it's a lot easier to just have higher gain and higher bandwidth. So is there a reason that you want your bandwidth so high as opposed to just trying to compute?
Great question. So the question was, well, look, there's always kind of this trade-off for this game you can play, right? You can say, well, let's say that indeed I start not settling as well. Can't I always just increase my gain to compensate for it? Okay? Well, yes and no. So it depends on exactly how clever you are. And in fact, this actually very much touches upon the very next topic. Okay? Because notice, I've been mostly focusing on what happened right here. But remember, there's always this, let's say, long tail on the other side. So the problem is that if you just make your bandwidth very, very slow, but then up your gain, what will eventually happen is that basically you'll be remembering so many of the previous bits that you really just have no chance of crossing the threshold. Okay? If, for example, all of the previous bits were the opposite of what your bit should be. Now, having said that, in this very specific example, where I assume that the channel was absolutely perfect, you will find, if you really did an optimization of what's the best gain versus bandwidth, you'll find that this 2/3 number is not the right answer. Okay, I'll tell you that now. It's actually going to be lower than that. However, you have to remember that there's always going to be extra both amplification stages and poles in the rest of the system. If you then do a more detailed optimization, you'll find that this 2/3 number is basically about right. And that's kind of for the overall bandwidth. And that's really balancing out essentially not just the settling error, but even the residual intersymbol interference, so the residual sort of time spread we were talking about a second ago. Yes? Okay. So in the project, I think this will be true throughout basically the whole thing. You should assume that I've been very nice to you and you can decide to sample wherever you want. In other words, you can try and sample at the quote-unquote optimum time. That's not to say that in reality that would actually happen, but for the project, as I said, I'll be nice to you guys and you can make that assumption. Well, when you say the middle, it's typically, let's say, in the middle of the quote-unquote eye diagram. But if you think about, let's say, on this, on this picture right here, it's actually right at that peak point, right? Which if you sort of lined it up, if you took out the channel delay, that would actually be kind of at the very edge of that transmitted bit. Because that would give you the most time to actually settle the amplifier. So I guess, depending on whether you like thinking about eye diagrams or voltage waveforms, in eye diagram, it's usually in the middle. Okay, so unless there's more questions on that, let's go ahead and move on to the next set of lecture notes. And so here there's really kind of two key topics that are actually very strongly related to each other that we're going to talk about very briefly. So the first is kind of coming back to this picture here, which is we spent quite a bit of time talking about the noise and the minimum signal magnitude. But as we've already hinted at several times, there's also this so-called intersymbol interference issue that we have to deal with. So let's look at that more carefully. So it turns out the best way to really think about that is to just take a bit at our transmitter and then pass it through our channel, meaning pass it through the transmission lines and stubs and etc., and see what's the analog voltage waveform that shows up on the receive side. So blue is what I've transmitted, green is what shows up on the receiver, and these black dots, those are sort of the analog values I would get if I sampled the received signal exactly at sort of, let's say, the quote-unquote optimum time and spaced by one t-symbol from each other. So remember, at the comparator is clocked. It only looks at those particular time instances. So these black dots are kind of the analog values you'd get at the input of the comparator if you sampled it at exactly these bit-spaced times apart from each other. So there's a couple of things, of course, to notice here. The first is that, my nice, clean, sharp blue pulse got spread out in time. Right? That's just the low pass behavior of the channel. The second that you might notice is that there's kind of these funny wiggly things out over here. Those are usually associated with some kind of reflection or some kind of stub somewhere in the system. So that's energy kind of bouncing off some discontinuity and ringing around inside of your channel for some period of time. That's usually what causes these extra wiggles out over here. But let's first focus on sort of just the time spreading part of it. So, just from a terminology standpoint, the value that you get at that, which is essentially the largest one, is typically what's referred to as the cursor. Okay, and I'm going to call it the cursor for the following reason. All of the sort of samples you get after that time are all considered to be the post-cursor. And all of the samples before it are what's called the so-called precursor. So cursor is just kind of a reference point. But usually it's the reference point that you say, well, if this is the cursor, then usually when you're asking about when you would sample your data, you'd try and sample it here, right? Because most of the information about that data is showing up at that particular time instance. Now, let me ask you guys a question. Is anything sort of physically busted in the fact that I actually do have a precursor here, meaning that I have some significant amount of energy showing up before my main thing actually did? Or is that totally okay? Okay, you said it's fine. Why is it fine? Yeah, okay, so you actually gave the very simple answer, which is absolutely correct, which is, well, hey, look, yeah, this showed up before this one did, but still largely delayed from when I sent the data in the first place. So I'm not violating causality or anything like that. This information is indeed associated with this. It's just showing up a little bit earlier than this one is. Okay, so now just maybe for the sake of completeness, does anyone know the sort of physics terminology for why something like this happens? Yeah, dispersion. Okay, so dispersion usually says that the high-frequency components arrive earlier than the low-frequency components. Exactly what's happening here. So indeed, you can have both precursors and the so-called postcursors. Okay, so now let's go and see what this does to us from a communication standpoint. So in order to sort of make that clear, what I've done here is I've drawn not just one bit, but I'm actually going to draw several bits. And in particular, what I'm going to be doing is trying to send something like a 0, 1, 0, 1, and then a bunch of zeros data pattern. So this green curve right here is just the analog waveform I got from sending this first one. And this blue waveform right here is the analog waveform I got from sending that second one. And so if I want to know what the sort of overall response looks like, all I have to do is take that green waveform and add it to that blue waveform. And in the end, what I'll get is this red waveform here. And that's, again, just a linear system. I can just take the two inputs, decompose them, and then add them back together at the end. Right? All right. So now here's the question for you guys. And by the way, there is, I shouldn't say an error, but there's a little bit of a sneaky subtlety in this particular slide so that you can't necessarily just read the text and come up with the answer I'm going to ask, or answer for the question I'm about to ask you. So if you received this red waveform, and you just used a simple comparator as your receiver, meaning it just decides if input is either a 1 or a 0, what digital bit stream would you receive from that red waveform? Okay, it depends. What does it depend on? There we go. Okay, it depends on the threshold you choose. So take your pick. Where do you want to put the threshold? Say that again? 0.4. Okay, sure. Let's put it at 0.4. And let me get the right color here. Okay, so if you put it at 0.4, and ignore the fact that my lines are not very straight. Okay, what would you interpret it as? Yeah, at the receiver, what would you interpret it as? Okay, you interpret it as 101. That's absolutely correct. Now, why can't you put it at 0.4? Why is that not really the right place to be? Oh, okay, so if I understood you correctly, I think you said, well, if instead of sending, for example, 0, 1, 0, 1, 0, 1, 0, I, for example, sent 0, 1, 1, 0, 0, then actually this wouldn't work anymore. That's correct. There's an even, let's say, simpler, more intuitive answer. Yeah? Okay, you said you're barely catching the tops of those peaks on the green line. That's correct, but I want even something, let's say, more immediate. So remember way back when we sent that, if I'm sending plus delta and minus delta, where do I want to put my threshold? 0. Okay, so in this picture here, where is quote unquote 0? It's at 0.5, right? Yeah, but remember, what's going to happen if I send, for example, an infinite stream of ones? Where is the analog waveform going to sit? On the receive side. It's going to sit all the way at 1. Right? If I send an infinite stream of zeros on the receive side, it's going to sit all the way at 0. Okay, so then you want to put it at 0.5. Exactly, I do want to put it at 0.5. So now, if I put it at 0.5, now what do I interpret everything as? Yeah, it's all zeros. So now I actually have enough quote-unquote intersymbol interference, meaning the added up weight of all of these sort of secondary kinds of things was big enough that it actually pushed all of my stuff below the threshold. Yes?
Well, I mean, it seems like if you put it at 0.5, even without intersymbol interference, you still get outcomes. Because like, if you just looked at, say, the green signal, that's all.
Yeah, okay, but so here's a little bit of a subtlety with this picture. Notice because everything is not, let's say, center biased, what's happening here is that in reality, if you really want to think about this, let's say the easiest way, what you should really think about is a 1 would really be something that basically adds a pulse from 0 to 1, and a 0 would actually be a pulse from 0 to minus 1. So what's really happening in this picture, basically both here and here, is that the way you should interpret this is that actually the fact that you sent, conceptually at least, an infinite stream of zeros or minus 1s beforehand is actually pushing this guy down. In other words, all of this ISI added up is actually pushing this guy to be lower than the threshold should have been. So that's why I said usually the easier way to think about this is actually to think of plus 1s and minus 1s. But that's why I said there's a little bit of a subtlety in this picture, which maybe for the sake of my own amusement, gave us some good questions to answer on this next picture. It's an excellent question, though. Okay, so again, the take-home message here is really that this intersymbol interference can very easily cause you to get bit errors. In other words, simply because of the fact that those information from either previous or even quote-unquote future bits is basically messing up the analog waveform that you receive, you no longer can just rely on saying, well, the thing was either above a threshold or below, because as you can see, there's no real unique good answer. Right? Depending upon what exactly I sent, that would actually change which threshold, ideally speaking, I would want to use to get the data stream back. Okay? So, I'm going to talk about sort of 2 at least conceptual possible solutions to this problem. And it turns out that neither one of them is going to involve increasing the transmit swing. And hopefully the reason for that is obvious, right? If all I did was took the transmit swing and increased it, right, all that would do is just scale this entire y-axis there. But it wouldn't change the fact that, for example, this piece of the green bit is messing up, for example, that piece of the blue bit or vice versa. Okay? In other words, scaling the transmit swing, if you have an ISI problem, really won't solve it. In other words, if you're already making mistakes due to ISI, you can increase the swing as much as you want. It's really not going to solve the problem. So, given that that's the case, let's say one of the only options you have, or maybe not only option, but the, let's say, most effective and common option, is to do what's called equalization. Now, this may sound a little bit hokey at first, but this is indeed extremely common. So the idea is the following. Okay, let's say indeed I have my transmitter. I take that, I feed it through my transmission line, or really more generally my channel. And then at the receiver, before actually doing that slicing operation or the comparator operation, I'm going to feed it into what's called an equalizer. and then really feed it to my, let's say, normal receiver. So if I think of this from a kind of linear system standpoint, let's assume that that transmission line had some filter associated with it, that I'm just going to call it h of s. All this equalizer, at least conceptually, is trying to do is say, well, you know what? If I have some filter, but it's some linear filter, then as long as that linear filter is not too messed up, and we'll talk about that more in 1 second, all I have to do is basically build the inverse of that filter, right? So that by the time I get to my receiver, if I look at a bit that was transmitted here, and then pick it up right there, well, if indeed I built the exact inverse of that channel response, whatever I sent here should be exactly what I sent here, of course, just with some extra noise on it. So in other words, if in the frequency domain I literally just undo whatever badness was done in the channel, then I should be able to make it so that rather than getting these spread out and wiggly waveforms, I could indeed get exactly those square waves back. So let's think about this a little bit more carefully. So in particular, if you remember, we said several times already that the link channels we deal with typically are low-pass filters. Right? So if I looked at my sort of channel response, the magnitude of it versus frequency, typically you'll see something that looks basically like this. And just as an example, let's just pretend that this is sitting at 1 gigahertz. And as an example, this is now a gain of 1. So if that's the case, and I wanted to build my equalizer, and by the way, for those of you guys who have played with any audio stuff, this equalizer is exactly the same as that equalizer, just slightly different usage. And really it's called an equalizer because it's just trying to make the response to all frequencies look the same. So if I wanted to indeed equalize this channel that I've drawn on the left there, what should my equalizer look like in the frequency domain? Yeah, it's a high-pass filter, but more specifically, so let's just say that the gain here was 1. So what would be like the DC gain of that high-pass filter? And let me just call this H EQ of S. Okay, it'd also be 1. All right, so then what else? Okay, then it goes up at what frequency? 1 gigahertz. Okay, good. And let's just say that this was 20 dB per decade. Of course, this should also be 20 dB per decade. All right, but so now I want to ask you guys a couple of slightly more subtle questions. So what we drew here was literally the inverse of the channel response. Like we literally just did, 1 over h of s. So now I want to ask you guys, do I actually have to do exactly 1 over h of s or not? In other words, can I still get my equalization functionality without exactly doing the inverse? Okay, you said I can use a lower DC gain. By the way, is it just DC gain that I can play with, or? Okay, great. So the first thing you can do, which hopefully should be obvious, is nobody said this has to be actually 1. Right? I can take the whole thing and scale it by some arbitrary constant. And to 0 order, nothing really changes other than just the magnitude of the signal coming out of the equalizer. That certainly works. There's no problem with that. There's another thing that we can, in fact, I will claim will actually have to change in order to make this work. So what's the problem? Okay, there is indeed normally delay through that. Let's not worry about that so much. Yes, Amit. Yeah, there we go. So you said you can't get this 20 dB per decade to increase forever, because in particular, what's the problem? Why, what happens if I let that increase forever? What does it imply? Yeah, exactly. It means I need to have infinite gain at infinite frequency. And so again, by the way, this is one of those cases, if you know how to do that, please tell me. I want the patent or whatever it is. But unfortunately, I don't think it's going to happen. So clearly, there's no way you can actually build this, right? There's no way you can actually get infinite gain at infinite frequency. So what this really says is that there's always going to have to be some finite amount of bandwidth that you use to actually build that equalizer before, just practically speaking, its gain is going to have to roll off. Okay? So typically the way that looks is the following. And I'm just going to redraw sort of our channel response and the sort of equalizer, or let's say the inverse, and then we'll see what the real equalizer would look like. So if this was our channel response versus frequency, where again, let's just say it did something like 1 gigahertz like this. We said that if we really did the inverse, of course, that would have looked like that. Right? So that would have just been H inverse of S. And if we want to look at what a real equalizer will do, well, I'm going to argue it's going to look something like the following. So let's just call that HEQ of S. Again, of course, I'm looking at the magnitude. So as we said before, at DC, the gain is kind of arbitrary. We can decide whatever we want it to be based upon how much swing we actually want coming out of this thing. As before, we're still going to want to put a 0 at 1 gigahertz, because that's the way we're going to start compensating for essentially the frequency roll-off of the channel itself. So the thing is going to start increasing there. But now, as we said before, we have to have a finite bandwidth. Right? There's kind of no way around that. Well, in practice, what that typically means is that the way these things will look, oops, and now let me try and draw it a little bit more carefully, is something like this. Okay? So this point here is basically the kind of bandwidth of our system. Where I'm basically saying beyond that, I'm not going to actually try and really literally maintain the inverse of the channel. But hey, I probably don't even actually have to, because I don't really have that much more information sitting out there anyways. So just if we were to follow a rule of thumb, let's say again we were at 6 gigabits per second, what would that sort of point that I'm indicating there be, where you roll back over? Is it 3 gigahertz? There we go, 4. Remember, I said 2/3. Okay, so indeed, it would be at, and again, this is just rule of thumb, at 4 gigahertz. Now, by the way, the thing to make sure it's clear to everybody, there are actually 2 poles there, not just 1. And that's very much linked to basically the way these things are built. So we're not going to spend a ton of more time on that today, because I do want to mention sort of one other option quickly before we break. But it's almost always the case that you can't really get a 0 without having a pole associated with it. And then on top of that, as we said before, anytime we build an amplifier or anything like that, it's also going to have its own pole associated with it. So the 2 poles that are there, one of them comes from just basically you can't have a 0 without a pole. And the other one really comes from the amplifier itself. So there are lots of actually very interesting design trade-offs in how you build these equalizers, particularly using analog circuits. If you're interested, come bug me. I can tell you a whole lot more about that. For this year's project, I decided, just give me 1 second. For this year's project, I decided not to focus quite so much on that as on some slightly different aspects. But if you sort of are tracking with some of the previous year's lectures, you'll see there's a whole lot more material on how you really build these equalizers. So yeah, question? So you're asking, does this sort of still need to account for the dispersion? In the simple example that I'm giving you here, where I assume the channel really was a first-order low-pass filter, I'm actually accounting exactly for the dispersion, because basically the magnitude response is uniquely linked to the phase response. In general, that may not necessarily be the case, and you may have to do something specifically to deal with the phase response. That's absolutely possible. Okay, so as I said, this is really to give you kind of a little bit of an idea about what equalizers are all about, and depending on how things go, you may have some opportunity to play with that in the project. But for this year, I actually wanted to have you guys look at a slightly different approach. And in particular, it turns out there's another solution that you can try and use to get around these issues that might be created by the low pass, or let's say frequency selective behavior of the channel. And so the way you do that is actually conceptually kind of simple and very similar to what we've talked about in the past. So if you think about it, so far everything we've been looking at has been a very, very simple digital communication system. It said we can always only send 2 levels, or really one of 2 levels. Either it's +1 or -1. But by the way, that's what's called a so-called 2-PAM system. PAM just stands for pulse amplitude modulation. So the trick here is because we're only sending those 2 levels, at every symbol time, we can only send one bit of information. Well, as an example, why don't we send 2 bits of information for every symbol? Now, the reason that actually is quote-unquote a potential solution to this so-called equalization problem is that if I'm now sending 2 bits per symbol, then for the same data rate, the actual amount of bandwidth I need to use is going to be half, right? And so if, as an example, that means that I can go from, and let me just go back, let me go back to this picture. If, for example, before I was sitting here, and now I can get myself to sit right there, hey, notice the channel actually looks pretty darn good now, right? Now, it turns out that there's no free lunch. Obviously, there's going to be a lot more complexity introduced by doing this, and we're going to talk a lot more about that on Thursday. But for our project, we're indeed going to use these so-called multi-level signaling, in particular for PAM. And again, the whole idea there is that rather than sort of try and deal with more of the equalization challenge by building these frequency selective circuits, instead we're going to trade off and try and tolerate more dynamic range in the signal itself directly, but not have to deal with the sort of frequency dependent effects. Okay? Make sense to everybody here? All right, so we'll finish with that for today, and we'll